Hello and welcome to another Tycho video. Today I'm going to be demonstrating how to recover lost satellites. Now lost can take on a couple of different meanings, which I will get to here in just a moment. But first I want to talk about a couple of the features that I will be using throughout this video. These are features that are available in the latest version 12 of the Tycho software. The first one being the monitor queue module, which helps you to automate the sky survey portion of it. And the second is the ability to invoke the fast follow-up routine. What that does for us is that if we do actually recover the object in that same night, we'd like to do a second set of measurements so that we can solidify the orbit and not lose it so easily again in the future. And with that, I will also have some examples of success that I've had with this sort of technique. So again, two different meanings here for a lost satellite. One is there could be some level of uncertainty in the timing portion of the orbital element. So the revolutions per day, for example, you might not know exactly what that parameter should be. And all that means is that, well, you might know where to point the telescope, but you do not know when the object will appear in the field of view. And the other is uncertainty in some other portion of the element set. So for example, inclination, eccentricity, and so forth. And that one can be a bit more challenging because then you do not know where to point the telescope exactly. You have to search a broader portion of the sky. So let's go ahead and take a look at visualizing these two different concepts. Okay, so let's go ahead and take a look at a way to visualize these two different types of uncertainties. So the first thing I can do is go to the satellites menu and choose satellite lookup. And what I want to do is retrieve a list of satellites in low Earth orbit. Again, just as an example. So I choose type equal low Earth orbit, and I click the add button. And what that does is it adds a filter to the query. Now, if I wanted to, I could also choose additional filters, for example, a filter on inclination, eccentricity, and so forth. But for now, we will just keep this fairly simple and straightforward. Then I click the perform query button, and when I do that, it returns the first 1,000 results. So here we have a list of approximately 1,000 objects. And what I would like to do is I would like to select one of these objects. So this is A1 asterisk. And if you are familiar with the international designation, the first two digits correspond to the year of launch. So this was launched in 1965. And as it happens, asterisk is the very first French satellite. So here is a Wikipedia article on this if you want to learn more about it. So for now, what I will do is right-click and choose Add to TLE Propagator. And as you can see, this presents a new window here. So we have currently one entry in this list. And when I right-click on this entry, I have a number of actions available to choose from. I can attach to Dataset, Session Planner, Satellite Viewer, Show Upcoming Positions, and so forth. So what I would like to do now is to attach to Satellite Viewer. So here is the satellite plot window. And as you can see, this is the orbit of this object. Now, if you are not seeing this particular view, you can always right-click and change the view. So I am using the top-down view here. And what I can do is I can hold down the Shift key and drag the cursor, and this allows me to look at a different viewing angle. I can also adjust the position slider here, so you can see the position of the object over time. Now, for the purpose of this visualization, the goal is to simulate some sort of uncertainty in the timing portion of the orbit. So I go back to this window, I right-click and I choose Show TLE Text. This is the two-line element, and this populates this portion of the window. The first thing I do is I change the designation. So I'm going to call it A2 just to differentiate it from the original object. And what I would like to do is I'd like to make a small change to the revolutions per day. So currently 13.49 revolutions per day. I'm going to make it 13.48. In other words, I'm going to slow it down a bit. And I can click Add New TLE to List. So now I have two objects that I can select and choose Attach to Satellite Viewer. So as you can see now, we have this view of two different orbits, just a very slightly different revolutions per day. And you can see the effect of that is that they have a slight delay in timing, a slight offset in when they appear. So if I change my view now, I can say sky coordinates are a deck, and this also is another way to look at it. So again, they share a very similar track. And the goal here is to demonstrate that even though I have some level of uncertainty as to when they might appear, I can still point my telescope at the predicted position. And at some point in time, that object will cross the field of view. So for example, I could point my telescope at this position and have some high degree of confidence that the object will appear in that field of view. So for example, I can again adjust the position slider and you can see what that looks like. Now, again, this is very close to the actual epoch of the TLE. So for example, if I go back to the top view here, you can see again, they are fairly close together. And that's because my start date is I chose now, and it just so happens that corresponds to very close in time to the epoch of the TLE. So for example, this is the epoch here. 2025 is the year and the 94th day in that year. So what happens if we start to compute the predicted position at a date farther out in time from the actual epoch of the TLE? So for example, I can choose a start date now plus a few days. So let's do 5 days from now. And then you'll start to see that they start to deviate more in offset. So here's how far separated they are, which is 5 days apart. And we'll add another 5 days to show what that looks like. So now they're even farther apart. And let's add 10 days to that. And they should be even farther apart than that. So again, even if you have a very small change in revolutions per day, that change starts to magnify the farther apart you get from the epoch of the TLE. Now another thing to demonstrate is if I go back to the TLE here and I make a slightly larger change, I change the revolutions per day to 13.38 for example, and I can delete the other object here. So I can attach both of these objects to satellite viewer. You can see with that slightly larger change in revolutions per day, even though I'm now back to the start date of now, they are farther apart due to that larger change in revolutions per day. But also we can more clearly see that the slower object, the one having fewer revolutions per day, also has a noticeably different altitude. We start to see a different altitude. So A1 being the original object at 1539 kilometers, and A2 at that same point in time has 1589 kilometers in altitude. So it is a higher altitude owing to the fact that it has fewer revolutions per day. So again, it can be interesting to visualize that concept. So again, that is what happens when we have some uncertainty in the timing component, is that again, they still share the same track, but we just have less confidence as to exactly when the object will present itself in the field of view. So the strategy there is you simply point the telescope where it is predicted to be, and you can stare at that field of view for some number of minutes or hours until it actually crosses the field of view. Now another uncertainty to look at is maybe not with respect to time, but instead some other orbital parameter. For example, what happens if we adjust the inclination of the object? So I can take the original element set and I'll give it a different designation here, and rather than 34 degrees, maybe it's 44 degrees inclination. So again, I can take these two objects here, attach to satellite viewer, and that's what that looks like, is that now they no longer share the same track. They have a different track altogether, and if you were to try to point your telescope at the same or the predicted coordinates, you might not have success because now they are deviated quite a bit from having the same field of view. So again, this is just a way to visualize those two different types of uncertainty. Okay, so let's go ahead and work through a few examples here. The first one is the deployment of the Guowang satellite constellation. Next we have Genfan 12, which is part of another satellite constellation, and finally DSN-2R, and this one could more or less be categorized as space debris because this is actually a rocket body. However, what makes this one interesting and sets it apart from the first two is that it has high eccentricity and is also in a higher orbit, so that eccentricity makes it a bit of a challenge to get enough observations on it during a single night so that you can compute an accurate enough orbit to follow it up on subsequent evenings. In fact, this is an object that I encountered serendipitously during one evening of a sky survey, so I thought it would be interesting to include it as an example. So with that, let's go ahead and start with the first example. Okay, so this first example relates to the deployment of the Guowang satellite constellation. I had checked my email one morning from a mailing list that I'm a part of, and the author of that email mentioned that a rocket had been launched that is going to deploy this train of satellites, and it would be interesting to observe them. And that author had listed two candidate element sets. So if I go to the TLE propagator here, you can see these first two items correspond to those candidate orbits. The first one being a 350 kilometer altitude and the other being 450 kilometer altitude, because the height of the object was not quite known at the time. So again, we have these two different orbits, and I can right click and show you what that looks like here visually. So that evening I went out to try and observe it, and it was already too late for me to capture the 350 kilometer orbit, but luckily I was still able to try to capture it if it was more closely that of the 450 kilometer orbit. So you can see here the progression in time. That's what the orbit looks like. And so I went ahead and set up the telescope and stared at a given field where the object would be expected to pass through, and I just so happened that I was able to find it. So in fact, the actual orbit, as I would later come to find out, is 1100 kilometers. And so you can see what that looks like here. So this is the 450 kilometer, the initially predicted orbit, and this is the actual orbit here. And so you can see that is a much higher altitude. You can see it here visually. And so again, that was very interesting because I was able to capture it, and it actually appeared just 6 minutes after the predicted time. So here you can see what this actually looks like in the images that I captured. You'll notice that the satellite train appears at the edge of the field of view. So this is at the first detection. Later on, I would go ahead and adjust the mount so that it would appear more centered in the frame. But anyway, I just thought this was interesting because this is the first time I had ever captured a train of satellites in a constellation deployment. Okay, so this is the second example. This is Junfan 12, which is part of another satellite constellation. Now, I did not originally set out to image this object. In fact, my original goal was to image Explorer 40. But as you can see here, I am using the Fast Tracker module. And what Fast Tracker module allows us to do is to easily detect streaked objects in a set of images. It also automatically matches those detections with known satellites. But as you can see here, there is one detection that could not be matched with a known satellite. So I get interested in that, and I right-click and choose Fast Follow-up. And what Fast Follow-up allows us to do is to predict where that object will be located 1 minute from now. So I paste those coordinates into the acquisition software. And 1 minute from now is just about enough time to allow the mount to slew to that position. Now, it also allows us to do a few other things to get ready for the acquisition as well. But the goal behind this, the purpose behind the fast follow-up is that we need to be able to collect additional observations of this object throughout the night so that we can compute an accurate orbit of it and therefore follow it up on subsequent evenings. So at this point, the mount has slewed the coordinates, and now I'm going to tell the acquisition software to collect another set of images. Usually I do 60 or 90 exposures 1 second each. And here you can see that the fast follow-up routine correctly predicted where the object would be located. So this is that object that could not be matched with a known satellite. So that's always very interesting to see. And you can also see that the monitor queue module is running in the background. So it is incrementing the count of exposures that it is observing in the acquisition folder. And there's also another satellite that happens to make a pass through this same field of view. So I go ahead and I stop the acquisition. And the way the monitor queue works is that after 5 seconds have elapsed where there have been no increase in the number of exposures, then it automatically launches another instance of the Tycho software. So you can see that here, another instance has launched, and it is automatically processing that set of images that we have just captured. So that allows us to streamline the acquisition process. We can more easily collect batches of images to follow up this object. So now what I'm going to do is fast forward a bit, a few minutes later on, and you can see I'm kind of repeating this process a little bit, but this is just to show you a second pass through. So I paste the coordinates of a predicted position into the acquisition software. And here you can see we're up against a little bit of a challenge, because now at this point in time, the object is going to be a bit lower on the horizon. You can see that there's a tree in the background, and there's also some clouds that have made an appearance. But I am optimistic as I'm doing this that I can collect additional measurements of this object. So the mount has now slewed to that position, and I tell the acquisition software to go ahead and start collecting another set of images. Meanwhile, there's another satellite that makes a pass through the field of view. Again, that's not the one that I am going to image, but the Tycho software is also now finishing up the previous batch of images, and it has identified 3 streaked objects. The one in the middle, that is the one that we are interested in. And now you can see that the object we are interested in has just now made an appearance in that field of view. Now the question at this point might be, how was I able to determine that this object is in fact associated with GenFin 12? And the answer to that is that I first took the measurements that I had generated that night, and I then computed a 2-line element for this object. In other words, I fit the measurements to an orbit, and I then shared that TLE with others, and one of them responded that it appeared to be coplanar with both GenFin 14 and GenFin 12. And as it happens, both objects had just recently undergone an orbital raising maneuver, and the published TLE that was selected for the matching routine had not taken into account this orbital raising maneuver. And you can see that with the high along track residual of 44 seconds. Meanwhile, the TLE that was published a day later did take into account the orbital raising maneuver, and you can see that with the much improved residuals. This is the TLE associated with GenFin 12. Now, out of this discovery, I made an improvement to the matching routine. So rather than computing a basic distance between the detected position and the predicted position, I now distill it down into 2 separate residuals, cross-track and along track. And importantly, each residual has its own separate tolerance. And you can see that here on this slide, where this is the improved fast tracker results, and it has these columns: object distance corresponding to the cross-track residual, and offset in seconds corresponding to the along track residual. And you can also see that it correctly matches the detection with GenFin 12. Now, the default tolerances for the matching routine are almost always ideal. You should never really have to change them, but in case you want to change them, they are configurable through the settings window. So you have ArtSet match configuration, and you have these settings here that you can adjust. And so you can see that the cross-track tolerance and the along-track tolerance, they can both be configured as desired. Now, this third example, as I mentioned earlier, is different from the first 2 in that it has a very highly eccentric orbit. So to demonstrate this, I go to Satellites, TLE Propagator, and you can see that it has an eccentricity of 0.72. The other objects we've looked at so far have basically a perfectly circular orbit. So if I want to, I can right-click and choose Attach to Satellite Viewer, and you can see that it is only mapped out a small portion of the orbit. The reason for that is that we need to select a longer duration. So I'm going to choose 72 hours for the duration and replot the orbit. So you can see that's what that looks like. Again, very eccentric orbit. And if we want to, I could also include GenFin 12 just for perspective. So again, I can replot the orbit, and you can see that the two orbits here, what they look like side by side. So it can be interesting to do that kind of comparison. Now, I also want to take a moment to share with you what this object looked like the first time I saw it. This is using the improved matching routine, and as you can see, it did not match with any known object. So this is what prompted me to take a closer look at it, and I was able to generate additional observations on this object throughout that evening. So in this video, I have covered how to do an initial detection of an object, how to use the fast follow-up routine to generate additional measurements of an object in that same evening, and I will also plan to be doing another video that goes into more detail on how to make use of those observations. In other words, how to do initial orbit determination, differential correction, and so forth. So I think now is a good stopping point for this video. So thank you for watching, and see you next time.